Questions 21 through 25 on the 2019 Grade 12 AMC 12A. Let z be equal to 1 plus I over root 2. What is the value of this big long expression? Well, it looks like I've got z to the power of 1, and then z to the power of 4, z to the power of 9, z to the power of would be 4 squared, z to the power of 5 squared, z to the power of 6 squared, z to the power of 7 squared, z to the power of 8 squared, 9 squared, 10 squared, 11 squared, and finally 12 squared, which is 144. And then that will all be multiplied by this big long, which is pretty much just the reciprocals, 1 over z1 plus 1 over z4, 1 over z9, and so on. Okay, so what I want to do is just figure out some of these. Like, for example, z to the power of 2. Well, z is just this. But what about z to the power of 2, z to the power of 3, so on? Let's see what we get. Z squared, that's going to be, if I square that, 1 plus 2i plus I squared, which is negative 1, all over 2. And that just goes to I. Okay? Z to the power of 4, that's going to be I squared, which is negative 1. Z to the power of 8 is going to be negative 1 squared, which is 1. And then so on. Z to the power of 16 would be that squared, which is 1. Z to the power of 32 would be that squared, which is 1, and so on. So we get some pretty good numbers here. So now let's substitute those into here. Z to the power of 1, this guy, well, that's just z. Z to the power of 4, well, that is negative 1. Z to the power of 9, well, that's going to be z to the power of 8 times z to the power of 1, right? Like that. And since z to the power of 8 is just 1, that's just going to be 1 times z, so that's going to be z. Z to the power of 16 is z to the power of 8 times z to the power of 8, so that's 1 times 1. Z to the power of 25 is z to the power of 8 3 times, and a z to the power of 1, so that's 1, 1, 1, and z. Z to the power of 36 is 8, 8, 8, 8, right? So that's just 1. Actually, let's revisit that z to the power of 36. I believe it was z8, 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 z8. That's 32, and then I have to add a z to the 4th. So that's going to be 1, 1, 1, 1, and then negative 1. So that's going to be negative 1, actually. Just got to be a little careful here. So far I'm doing good. And then let's just keep going here. Z to the power of 49, that's going to be z to the power of 48, which is a multiple of 8 times z. So that's just going to be z. Z to the power of 64 is a multiple of 8, so that's just going to be 1. Z to the power of 81 is z to the power of 80 times z, which is going to be a multiple of that, so 1 times z. And then z to the power of 100 is z to the power of 96 times z to the power of 4, and this is a multiple of 8, so that's just going to be 1 times negative 1, so negative 1 for z to the power of 100. And then z to the power of 121, well, that's z to the power of 120 times z, so that's just going to be z, since z to the power of 120 will be 1, since it's a multiple of 8. And then z to the power of 144, that is divisible by 8, I believe. Yeah, it is, because that goes in 18 times, I think. So that would be just 1. Okay, so we got that. And then this one will just be reciprocals. So it'll be 1 over z, negative 1 plus 1 over z plus 1 plus 1 over z, minus 1 plus 1 over z plus 1 plus 1 over z minus 1 plus 1 over z plus 1. Okay, so let's see what we get. 1, 2, 3, 4, 5, 6 z. And then negative 1 plus 1, that cancels negative 1 plus 1, negative 1 plus 1. Oh, those cancel. Okay. And then here we have 1, 2, 3, 4, 5, 6. So 6 over z. Negative 1 plus 1, negative 1 plus 1, negative 1 plus 1. Those cancel. So it looks like that's just going to be 36, and the z's cancel, and that's it. So 36 is the answer to 21, and that would be choice C. Circles W and Y, whatever symbol that is, both centered at O, have radii 20 and 17 respectively. Equilateral triangle ABC, whose interior lines in the interior W, but in the exterior of Y, has vertex A on W, and the line containing side BC is tangent to Y. Segments AO and BC intersect at P. BP over CP is 3. Then AB can be written in the form M over root N minus P over root Q. What is M plus N plus P plus Q? Here is a very helpful diagram that illustrates the question exactly the way it is according to the information in the question stem. So now we will start. The first thing, of course, is this right here, that BP to CP is in the ratio 3 to 1, basically. So from B to P, let's say from here to here is 3, well, 3x, let's say. And CP, this little guy, is going to be just x. So that basically means that that whole side, since it's being called S, it's equilateral. So that's S, and this is S, and that's S. So S is also equal to x plus 3x. So S is equal to x plus 3x, and therefore S, which is the length of the side, is equal to 4x. I can also write x as S over 4. And then I will try to get a expression for this height, and I can do that pretty easily using 30, 60, 90 triangles, because that's equilateral, so that's 60 and that's 30. So if I call this H, which is basically right there, AD, then I know this is S. So I can easily get an expression H over S is the equivalent of root 3 over 2, since that is a 30, 60, 90 triangle. So that means that H is equal to root 3 S over 2. Okay. We can now proceed. The first thing, of course, is try to get some sort of a relationship with the Pythagorean formula, because we've got a bunch of right angles in here. As you can see, there's one here, since that is a altitude, and then we've got another one here that goes from O all the way to the tangent point. They told me that the line containing side BC is tangent to that circle. So this is the line containing BC, and it's tangent to that circle, and that's why that's 90 degrees. Okay, since we have that, let's figure out at least one Pythagorean relationship, and I'll start with AP, which is my altitude right there. So AP squared will be equal to this altitude, which is AD, which is h squared, and then this little guy. Well, this isn't drawn to scale, because if this cuts the base in half, it would be 2x and 2x. So this would be 2x, and this would be 2x. And since this is already x, this is going to be x. But that's okay. So that means that it's going to be h squared plus x squared, where this is AP. All right, well, h we know in terms of s. We've got that right here. So that's going to be root 3s over 2 all squared. And then x we know in terms of s right there. So that's going to be s over 4 all squared. So this looks like 3s squared over 4 plus s squared over 16, top and bottom by 4. And I get 12 plus 1, 13s squared over 16. and therefore AP would be root 13s over 4. Okay, so that is a pretty decent start to this question. Now let's look at some similar triangles. And similar triangles will help us, and in particular I'm going to be looking at triangle OQP, and that is similar to triangle APM. We'll just call this point M, this guy right here, like that. Now they're similar because they have the same angles. This angle obviously is the same as this angle since they're opposite angles, and then this is a right angle, that's a right angle, and therefore the third angle must be equal. So here we go. That means OP over OQ will be the same as AP over AM, like that. So OP would be equal to 17 times AP, which we just calculated as root 13s over 4, and then all over AM, and AM is the height, which is root 3s over 2. Root 3s over 2. All right, so let's move this up a bit. And now if I were to simplify that, that simplifies to 17 over 2 root 13 over root 3. The s's will cancel. Okay, we are now, believe it or not, into the final step of this challenging question. The final step is as follows: OP plus AP. What is that? Here's OP and here's AP. That line basically that connects O to A. And that of course is equal to OA. And OA is the radius of that big one, and the big circle was 20. OP individually, well, OP is this. So 17 over 2 root 13 over root 3. And then AP was this guy. So root 13s over 4. So this will allow me to solve for S, which is the side of the triangle. And the side of the triangle is what they want me to figure out, which is AB. All right, so let's do that. We've got basically this to figure out. Let's get a common denominator first. So that's going to be top and bottom here by 2, top and bottom here by root 3. And that's going to be 34 root 13 plus root 3 root 13s. And then I can bring that 4 root 3, cross multiply it to get 80 root 3, like that. Okay, so this is root 3 root 13s, and this is 80 root 3 minus 34 root 13. So now let's divide through. 80 root 3 divided by root 3 times root 13 minus 34 times root 13 over root 3 root 13. So this gives me, the root 3's cancel, so 80 over root 13. And here the root 13's cancel, so 34 over root 3. Now that is in that form, m over root n minus p over root q. And they want me to figure out m plus n plus p plus q. So that's going to be 80 plus 13 plus 34 plus 3. And that is 130. So the answer to number 22 is E. Define binary operations star and diamond by a diamond b is equal to a to the exponent log of b to the base 7, and a heart b is a over 1 over log of b to the base 7 for all real numbers a and b for which these expressions are defined. The sequence an is defined recursively by a3 is equal to 3 heart 2, and an is equal to n heart times n minus 1 diamond an minus 1. Okay, for all integers n greater than or equal to 4, to the nearest integer, what is the log of a 2019 to the base 7? So let's work with this. A heart b, that is equal to a over 1 over log of b to the base 7. Now we can use log rules here. A lot of log rules are being used, so familiarize yourself with log rules. And the first one log rule is that you can change these numbers, and when you do, it becomes a reciprocal, so it becomes the log of 7 to the base b. So that's the first log rule. And then now let's talk about a3, since that's where the recursion begins. That's 3 heart 2. Okay, so let's see, what will a4 be? a4 is going to be using this rule. So let's use that rule. That's going to be 4 heart 3, entirely based on what they're giving me, and then times this diamond of a3, like that. Okay, so 4 heart 3, that I'm going to use this rule here, but I simplified that rule to make it look like that. So that's going to be 4 to the log of 7 to the base 3, and then the diamond of a3, and a3 is 3 heart 2. Okay, and 3 heart 2 is going to be using, again, this rule. It's going to be 3 to the log of 7 to the base 2. And this is, of course, 4 to the log 7 to the base 3. All right, let's continue here. So now I've got to go back to my diamond rule. This is the diamond rule here. So that's going to be 4 to the exponent log of 7 to the base 3 to the exponent of log of base 7 to the b. So that's 3 log 7 to the base 2. So I just got to be careful I don't mess this up. Okay. Now again, using log rules, we're going to keep this the same for now, 7 to the base 3. But this can come out front. It can come out front like that. So it's going to be the log of 7 to the base 2 times the log of 3 to the base 7, like that. Okay, now at this point, anything that we can do here? Well, we can use a rule that, again, gives a reciprocal, and that is going to involve these guys right here. If you switch the numbers, this one stays the same, 7 to the base 2. But if you switch the numbers 3 and 7, it becomes in the reciprocal. So log of 7 to the base 3, like that. So now we've got to multiply this exponent by that. And if you notice, this will cancel with that. So all we're left with is 4 to the exponent log of 7 to the base 2. And if you notice, that looks awfully similar to this when I use that. It is essentially 4 heart 2. And I hope you're convinced of that. Okay, so I got that a to the 4 is 4 heart 2. Now let's try a to the 5. So this was a to the 3, this is a to the 4. A to the 5 will be 5 heart 4, and then diamond 4 heart 2. And that was basically entirely based on that recursive formula. Okay, so now I want you to do the work here. Do the work. And when you do, you will come to a conclusion that this is 5 heart 2. So in general, a to the n is n heart 2. That's sort of the conclusion that we get. And n heart 2, if we go back and use this right here, is the same as n to the exponent log 7 to the base 2. So we got it all the way down to here. So now what do they want? They want me to figure out this whole thing. Log of a 2019 to the base 7. Okay. So they want me to figure out the log of a 2019 to the base 7. Okay. Well, the log of a to the 2019, according to this formula, it's going to be, let's just do it down here. A to the 2019 is going to be 2019 heart 2, and that's n to the power of log of 7 to the base 2, where n is 2019. So that is pretty much what that boils down to. So let's put that in there. So it's 2019 to the exponent log of 7 to the base 2, and that's all to the base 7. Well, that comes down there using log rules. So this becomes the log of 7 to the base 2 times the log of 2019 to the base 7. Now at this point, you use something known as the chain rule, the lesser known log rule. And that says if you've got this sort of situation, you can just write it as log of 2019 to the base 2. It's a chain rule. This and this sort of disappear. It's an interesting rule, actually. Very helpful, I think. So now this is it. This is all we have left. And we are asked what is the value to the nearest integer, since we don't have a calculator to our disposal on the AMC exams. Well, the log of 1024 to the base 2 is 10, and the log of 2048 to the base 2 is 11. And 2019 is a lot closer to 2048, so I'm confident that this is closer to 11. And that's all they wanted, just something that is nearest integer. So number 23, the answer would be D. For how many integers n between 1 and 50 inclusive is n squared minus 1 factorial over n factorial to the power of n an integer? Recall that 0 factorial is equal to 1. Let's think about this for a second. Before I dive into this, I just want to mention, if you had n factorial over, say, n squared, well, you could write this as n times n minus 1 factorial, and then the bottom you can break up into n times n. These two n's would cancel, and it would leave you with just n minus 1 factorial over n. So with that in mind, now let's tackle this guy. So that is step 2, n squared minus 1 factorial over n factorial to the power of n. Now for this, I want to make this into a better form. So what I'm going to do is I'm actually going to introduce a couple of things here. I'm going to keep what we have, of course, but then I'm going to introduce an n squared on the top and the bottom like that. When I do that, you'll notice that the top now becomes n squared factorial, very similar to what I did up top. And then the bottom now, we have this n factorial to the power of n times n squared. Okay, I'd like to work with this a little bit more. And the way I'm going to do that is by, again, adding n factorial to the top and bottom, and that will allow me to make a couple more changes. The first change is that I will just combine this one and this one to give me n factorial n plus 1, and then I'll just rearrange that n factorial and put it over n squared, and then this n squared factorial will remain the same. Okay, so now we want this to be an integer. Now, notice that if you just look at this term, that n squared factorial is going to be much greater than n factorial to the power of n plus 1. For example, if you had, say, n is equal to, say, 15, well, this part becomes 15 squared factorial, which is 225 factorial. And that's obviously going to be much greater than 15 factorial to the power of 16. So I'm fairly confident that this part will be an integer since the numerator is greater than the denominator. So now I have to concentrate on that. And that is the key to the question right here. I've got to concentrate on this guy. So I want that to be an integer. Well, let's see what happens. Remember, my range is from 1 to 50 for n. So let's see what happens with the first few. When n is 1, we get 1. When n is 2, we get 2 over 4. When n is 3, we get 6 over 9. When n is 4, we get 24 over 16. When n is 5, 5 is interesting because I think it's a little bit clearer that when it's a prime number like 5, it'll be 5 factorial over 5 squared, which is 5 times 5. And there's no way that this is going to be an integer because this 5 could cancel out with the first 5, right? But then there's no other 5 in the rest of the factorial, 4 times 3 times 2. So this is not going to be an integer. That's not going to work. How about n equals 6? That is going to be 6 factorial over 36. And that actually gives me 120. And you can keep going like this. And when you do, you hopefully will come to a conclusion that this n factorial over n squared is an integer when n is equal to 1, like we showed here, or n is not equal to 4, right? Because 4 didn't give me a value that works. Or n is not a prime, because for prime numbers it won't work. So basically, all the numbers between 1 and 50 that need to be eliminated are the primes and the 4. So that's pretty much how we're going to do this. So of the 50 numbers between 1 and 50, we get rid of that 4, so that's just one number, that 4. And then everything else that we get rid of is a prime number. And between 1 and 50, if you count them, there are 15 prime numbers. So 50 minus 1 minus 15 is 34. So 34 values of n between 1 and 50 will give this to be an integer, and therefore that whole thing will be an integer because it essentially was a modification of the original formula. And therefore number 25, the answer is D. Let triangle A0B0C0 be a triangle whose angle measures are exactly 59.999, 60, and 60.001. For each positive integer n, define an to be the foot of the altitude from an minus 1 to the line bn minus 1, cn minus 1. Likewise, define bn to be the foot of the altitude from bn minus 1 to the line an minus 1, cn minus 1. and Cn to be the foot of the altitude from Cn minus 1 to the line An minus 1, Bn minus 1. What is the least positive integer n for which the triangle An, Bn, Cn is obtuse? Obtuse meaning that one of the angles is greater than 90 degrees. All right, so let's draw what is an equilateral triangle, because it's very close to being an equilateral triangle when you first start out. If you look at the angles, they're very close to 60, 60, 60. Not exactly, but very close. So now let's work with this. Let's label it first A0, B0, and C0. And then the definition, entirely based on what's written in the question, is that you're going to draw altitudes. So first, let's draw this altitude. That's, of course, a right angle. And then draw another altitude that hits there, right angle. And another one from there to the other side, right angle. And when you do that, you get A1 here, B1 here, and C1 here. And they're saying that together those form a triangle. So this is the triangle it forms, and this is the first one, A1, B1, C1. And they want you to figure out the angles, and then eventually there's going to be a triangle where one angle is greater than 90 degrees. Okay? So there is a little bit of a technique, and that is making these cyclic. So I'll just draw in the first circle to illustrate how you make it a cyclic quadrilateral. So there you go. I've taken this quadrilateral right here, and I put it entirely inside a circle to illustrate that it's a cyclic quadrilateral. And then now, if you notice, this angle, it originates from those 2 points on the circle. And so does this angle. So because they originate from the same 2 points that are on the circle, the same arc, I guess, on the circle, those 2 angles will be the same. So if this is theta 1, this will also be theta 1 right here. Okay, so let's do the same thing, but this time on another circle or another quadrilateral. And there we go, here's another one. This time I've taken this quadrilateral and I've inscribed it into a circle. So in the same way, if I look at this angle, it starts from these 2 points, and then I take the same 2 points and create another angle. And when I do, those 2 angles will be the same. So if this is theta 2, this will also be theta 2. So that's theta 2, and that's theta 2. This is theta 1, and that's theta 1. All right, so now let's start calculating some of the A1, B1, and all that stuff. So this was 90 degrees, right? So this is also 90 degrees here. So that means that if you look at this triangle right here, theta 1 is equal to 90 minus angle A0. This is angle A0. And in a very similar way, if you look at that triangle, that's also a right triangle. This is a right angle. So theta 2 is also equal to 90 minus A0. So if we add them, theta 1 plus theta 2, they would be 90 minus A0 plus 90 minus A0, so it's 180 minus 2A0. Okay, so now we're ready for A1, B1, and C1. A1, that angle. And A1, that angle, is right here. It basically is equal to theta 1 plus theta 2. And that is 180 minus 2A0. Well, they've given us the angles, and so let's just assign them. A0 I will call 59.999. B0 I guess I can just call 60. And then C0, I can call the other one 60.001, like that. Okay, so in a very similar way, B1 would be 180 minus 2B0. And if you do that math with B0 equal to 60, that's just 60. And then this one, I can actually get a numerical value since A0 I've assigned this. 180 minus 2 times 59.999, it would give me 60.002. And finally, C1 would be 180 minus 2C0, since it would have pretty much the same pattern of calculation. And C0 is 60.001, so that would give me 59.998. Okay, and then you just keep going. Again, A2, it would be the same principle, 180 minus 2A1. And if you do that, you will get 59.996. B2, well, that's just going to be 180 minus 2 times B1, and that's just going to be 60. And then C2 will be 180 minus 2C1. And if you do that math, you will get 60.004. Okay, so at this point, I hope you can see some sort of a pattern. If you can't, that's okay. I will just make a little table here. We've got n, which it could be 1 or 2 and so on. And then we've got our angles. So for example, for 1, it's A1, B1, and C1. And then what is the largest angle? Because we want eventually to get an angle that's greater than 90. All right, so let's look at this and see. It initially may seem like this would take absolutely forever, but if you look at the answer choices, it's actually not that bad, the highest being 15. Because we're going up by such small values that it may seem that it would take, hundreds of iterations to get above 90. But it obviously can be done in 15 or less. So let's see. For when n is 1, the largest angle was this guy. So 60.02. 002, I should say. When n is 2, we have A2, B2, and C2. And as we calculated here, the largest was this guy, 60.004. And it looks like it's doubling. And I'm confident of that because when n was 0, we had A0, B0, C0, and the largest was, well, the largest of A0, B0, and C0 was this guy, 60.001. So 60.001. So as you can see, it is doubling. So for A3, B3, and C3, it would just be 60.008. What's doubling actually is not the full number. It just seems to be that part of the number that seems to be doubling. Okay, so let's just keep going. I'll just do it really quickly. So this is going to be 60.016. When it's 5, it'll be 60.032. When it's 6, it will be 60.064. When it's 7, it will be 60.128. It seems like you're never going to get to 90 within 15, but it tends to, the magic happens very quickly. Kind of reminds me of compound interest when you're investing. So number 9, 60.5. Sorry, this was 256. Now we have 512. Number 10. Now we're getting above 61. Ooh, okay, a little bit of progress. 11 would be 62.048. 12 would be 64.096. 13, 68.192. 14, 76.384, and the 15th is 92.768. There you go. AN, when n is 15, gives you an angle that is greater than 90. So, very interesting question. Number 25, the answer is E.